Okay, composition and inverse functions. A composition. Well, if you have f and g, and there are two functions, the composition of f and g is f, and that's supposed to be a little circle, og. This is called the function of f of g. It's also written as f of g of x is also written as that we're taking the function f and we're plugging g in everywhere as I see x of f. It's going to be easier for me to show you this here in a minute. If we are looking for its domain, we know that we need to know what's the domain of the g function when we plug it in there. That will determine the function of the g function, and the end result will determine it. The best way is going to be for me to give you a particular problem and just work it out right quick. Let me see, did they have one for me? No, okay, I'm gonna have to make one up, so it might be a little yucky, but bear with me. So say I have this function of x, say it's 1 over x plus 2. Let's do that. And I have this g function of 2x plus 1. All right. And I said, let's take the function of g. All right. The composition function f of g says that I'm going to take my f function, and everywhere as I see x, I'm going to plug in the g function. Well, let's rewrite it. Here is my f function. And now we're going to plug g into that function. Okay. And now let's use our regular math and let's get it cleaned up and determine what this new function is called. So I have 1 over 2x plus 1. There's nothing in front of this in parentheses. It's going to change anything because it could have been a negative x here. And then that meant everything here turned into a negative. But in this case, I didn't do that. So I can drop the parentheses, combine like terms. Well, this has an x on it. This one don't. So these two go together. So now I have 2x plus 3. This is my new function. There's not a whole lot more I can do. I cannot reduce it. I don't know the value of x. I just know this. So I know this much. However, we need to know its domain. A domain of a function is what's going to cause it. We want to find the numbers that's going to keep it as a real number. Okay. So one rule is you cannot have 0 in the denominator. There's a bunch of things you can't have in the denominator. Let me just do this right quick. In the denominator, which is the bottom of the fraction, right? You can't have 0. You can't have square roots or nth roots, whatever it may be, negative numbers. You can't have fractions. You can't have imaginary numbers. However, all of them except for the 0 can be worked out. Oh, you can't have decimal. I'll probably come along and come up with more. Can't have decimal in the denominator, but we can work with those. There's a mathematical rule that we can apply that's going to fix these here. However, not with 0. When you got 0, there's nothing you can do about it. So we need to know what's the domain. The domain is what's going to determine that's going to keep this as a real number. Well, we're going to take this f of g of x, and we're going to take the denominator, which is 2x plus 3. We're going to set it not equal to 0, and we're going to solve. And when I do that, I have to subtract 3 from both sides. Now I got 2x equals -3, divide by 2, divide by 2. Now what do I know? I know that x cannot equal a -3/2. Because if it does, that goes to 0. So my composition function, my new function, says my domain is going to be -infinity. Because if I want to draw it on the number line, it might help you. I know that I can have all points to the left of it. I can have all points to the right of it. I just cannot include this point. So I can write it as -infinity to -3/2. And we're going to say it's going to union because we're talking about both sides of it. And if you notice, I used a parenthesis on the -3/2, that's because we're going up to the point we're not going to equal it. If we was equaling it, I would put a bracket on it. Okay, so I know the domain for this function. However, since we are plugging a function into a function, we have to go back and look at the function we plugged in, because it could change this new domain. It could change it. Well, what is that function? G of x, we said, was 2x plus 1. Let's see it now. 2x plus 1. If you notice, this is a polynomial. This here doesn't have a root in it. It doesn't have a fraction in it. Therefore, it's all real numbers. So this here is not going to change what this domain is. However, if this had something involved that would cause it to be like a root or a fraction, then we have to factor that in. How do I know it's all real numbers? Because it don't matter what I plug into x in this one here, I'm going to always yield a real number, a negative, positive, whatever it is, it's going to be true. If we have an even root, like a square root, the fourth root, dot, 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 and so on, this one's going to have restrictions, because you cannot multiply something an even amount of times and come out with a positive number. So I'm going to come back to this one here in a minute. Let's talk about the odd roots. If I had a third root, a fifth root, and dot, 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 these are all real numbers, because it doesn't matter. I can multiply something an odd amount of times and get a negative number. I can multiply something an odd amount of times and get a positive number. So it doesn't matter what my radicand is. It could be a negative number inside. It could be a positive number inside. However, on the even roots, you can't have a square root of -4. This is where our imaginary number comes in, because this is not real. So I know that square root of -1 is I. It's imaginary. So therefore, this would become 2i, right? When we take the square root of both of those. So whenever we're looking for the domain of the function, and it has an even root, we have restrictions. If it has an odd root, you're just going to save a lot of work. You're just automatically going to say it's all real numbers for the domain. So let's do one right quick. So let's say I have g of x equal to the square root of 2x plus 1. Then that means that this is an even root. I have to take what's in that root, the radicand, and set it greater than or equal to 0, because it has to be bigger than 0, or it can equal 0, right? If it's less than 0, then it's going to give me a negative answer. So that's how you set it up. So now let's solve for x. Well, I'm going to subtract 1 from both sides. And guys, back to the basic algebra, I need a coefficient of +1 on x. If this was a -2 here, and I divided by the -2, remember this would have flipped. In this case, it's positive, so I'm not going to flip that. Okay. So that worked out. We're just going to divide by the +2. Again, if it was -2, it would have flipped that. So I got x is greater than or equal to -1/2. This means that when I plug in this -1/2 into this here, I'm going to get 0 as an answer, right? And that's okay. We can have a square root of 0. That's just 0. So that means I'm going to set it up like this. How do I know what's going right here? Because of this. This says my x is equal to or greater than. Then that means we're going off to positive infinity. However, if it was less than or equal to, then we would have set it up like that and then went. Okay, but it wasn't written that way. Okay, so that is composition functions. They're pretty fun. There's some formulas to work out. Let's talk about one-to-one. So definitely look over the PowerPoints. One-to-one, if a function has no two ordered pairs with different first coordinates and the same coordinate, then the function is one-to-one. All this is saying is that it cannot have no two ordered pairs with different first. coordinates. Here, I just read the definition. So 1-to-1. The best way for me to explain to you a 1-to-1 by using this math is if I can take the inverse of it and it gives me back, then it's 1-to-1. Okay. So if I have f, some function of f, let's say 3x plus 1, and we take the inverse of it and it yields out me with this function that is, let me just show you it here in this minute, then that means my inverse function that makes it 1-to-1. Okay, so I was looking for an example because I didn't want to make it up because I really wanted it to come out as an inverse. And so let's do this. Let's say g of x is equal to 1, 3 plus 1. Let's do 3 minus 1. Okay, so we're going to find its inverse to determine if it's 1-to-1, okay? I'm going to take this f function here, take the inverse of it. If it gives me back my g, then it's 1-to-1. So in order to take the inverse, we have a rule. We're going to rewrite the f of x as y, because we know it's equal to y, right? So let's rewrite it. Second, we're going to switch the x and y. Over here. Now we're going to solve for y. So when we solve for y, that means we need to get it by itself. So I'm going to subtract the 1. So now I have x minus 1 is equal to 3y. What am I going to do now? I'm going to divide by 3 because we need a positive 1 coefficient on y. And you can write it as x minus 1 over 3, or you can write it as 1/3 x minus 1/3. I mean, either way is correct, okay? However, here's the thing. This here is my f inverse. Right? Is this that? Well, no, because this here is actually 1/3 x minus 1. That is not the same as this. So therefore, this is not 1-to-1. However, if I took the inverse and I did these rules, it gave me back what this is, then it would have been 1-to-1. And in here, we have a really good example. And we got some graphs where you can determine 1-to-1. And I was looking, let me do this example right here, and this pretty much will wrap it up. So let's find this one. So we have f of x is equal to the square root of x minus 1. And we're going to find its inverse. And then we're going to graph it. And then I'll be able to show the 1-to-1. So I'm going to find its function, or inverse, I mean. That means I got to replace this to y. That means I got to switch. And this means I need to solve. Well, when I solve, I got the square root going on here. I got to undo it because y is inside it. I can't solve for y as long as it's inside that square root. So what I know is I can raise it to the power. If that was a cube root, I'd raise it to the 3rd power. So what I do to one side, I do to the other. So now I have x squared is equal to y minus 1. Let's add the 1 to both sides. And now my f inverse of x is x squared plus 1. So when I go graph this, my f of x, square root of x minus 1, when I go graph it, what we're going to do is plug in points for x. So if I plug in 2 for x in here, what do I get? I get square root of 1 for y. So now I know the order pair 2, 1. So that means it's 1, 2, right? Go up 1, right? So we're going to plug in 1. What happens when I plug in 1? We're not going to say it's on the, because it's not on the line, right? We got to find where it hits the line. So if I plug in 1 here, I get 1 minus 1. So now I got order pair 1, 0. So I can come and say, okay, right here. So that means this line will look like this, right? Because of the square root, this is the function we're going to get. Now, when we plug in its inverse, right, we're going to do the same thing. We're going to plug in some points. If I plug in 1 for x, I get 2 for y. And if y'all need me to plug it in and show you what do y'all need me to plug in showing you what I mean by plugging in something for x and then coming out with the y?
No, I follow it.
Okay. If I skip something, y'all let me know. I don't care to go back or add it and keep all the middle points in there. Okay, so we got order pair 1, 2. So I'm going to tell you that this is the inverse function. And remember, when I said it's the inverse function, what happens? The orders flip. Inverse tells me y becomes the x coordinate and x becomes the y coordinate. So this means here that it's 1, 2. So I get the inverse. Let's draw a dotted line. And you just keep plugging the points and this goes out that way. Whoops, yeah, goes out that way. My drawing's not great. But definitely review over this section and email me with any questions you have. I'm going to stop the recording.